Assalamu alaikum wa rahmatullah. Good day, everyone, and welcome to my YouTube channel today. Today's video is about the energy stored in a capacitor. We've already established that a capacitor stores electric charges, but because charges are carriers of electricity, we can infer that capacitor stores energy as well. Okay. um, Remember that work done to do some amount of work, you need energy. So this is why energy and work are given the same unit. So we are going to use work done. Okay, because if you connect a capacitor and you are storing charges in it, you are doing work on the capacitor. That work done on the capacitor is equivalent to the energy stored in the capacitor. So we will be using W as the work done, and that also means energy as well. Okay, I'm going to use parallel plate capacitor as an example. If I have this plate and I have the second plate here, then I connect this to a positive terminal of a battery, and then this one I connect it to a negative terminal of a battery. We know that this will store positive charges and this one will store negative charges. The charges are of equal amount but of opposite sign. Okay, to store this one will store plus q, this one negative q, of course. Now these charges are not stored all of a sudden. It has to take some time. So the potential difference built up from 0 to a maximum value V, which is the voltage of the battery here. The PD between this plate, okay, this plate is at high potential, this one at low potential. The PD increases from 0 to a maximum value of V. Okay, PD across this, the maximum value is V. Now it means electrical work has been done in storing these charges. How do we calculate that work done? We said work done is equal to average PD times charge times the charge stored. Okay, and now the average PD, remember we said it increases from 0 to V. So this is half. You take the initial and the final and you add the initial. It was 0 when you started, and then it reaches a maximum value of V. You see, then times q. Q is the total charge stored and on either plate, and that should be q, capital Q. So this one will now be half, and then you bring your q, and then you bring your v, because 0 plus v is v. So this means the work done or energy stored in a capacitor is given by half qv. This is the formula we use to calculate the work done or energy stored in a capacitor. You can also derive this using integral calculus. At any point, the work done at any given point is given by the charge stored, the total charge stored, divided by the potential difference at that instant. Multiplied by the potential difference at that instant. So if you want to get the total work done, this one becomes D, then becomes W. Then you have to take the integral here or on the other side, and then the lower limit is 0, the upper limit is V, because as we said, the voltage increases from 0 to a maximum value V. So the lower limit 0, upper limit V, and then you have Q dV. Good. Remember that there is a formula that says Q is equal to CV, right? So instead of Q here, you can substitute CV for Q here. So this is equal to integral 0 V and then CV. This is your Q, and then you still have dV. Now C is a constant, bring it out. C out of the integral, then you have from 0 to V. Inside you have V dV. If you integrate V with respect to V, you have V square over 2. So this is equal to C into V square over 2, okay, and the lower limit 0, the upper limit V. Now the next thing is that this will be C into where you have V, you put V, so you have V square over 2 minus, then you substitute 0 for V here, 0 square over 2, and this one will give you 0. So at the end you have 1 over 2 CV square, okay, 1 over 2 CV square as the work done. Okay, this one and this one are not different, because if you remember Q is equal to CV, so put substitute CV for Q here and see what you have. This will be half into CV, and then you have V here. You see, this is half CV times V squared. So you have this one again. You see, now in a nutshell, whenever you want to calculate the work done or energy stored in a capacitor, you use this formula: work done is equal to half QV. Sometimes you will be given the Q and the V, so you don't have to get anything but this formula, substitute and get your result. But sometimes you may not know Q. If you don't know Q, remember this formula: Q is equal to CV. Substitute it here. If you do that, I'm going to call this one equation 1. If you don't know Q, substitute CV in the formula, and then you have work done is equal to half into QV, CV, and then CV for the Q, and then you still have V there. So this is half CV squared. So you get the second formula: work done is equal to half CV squared. I'm going to call this one equation 2. If you look at equation 1 and 2, they both have VV in them. What if you don't know V? If you don't know V, go to equation 1 again, and then use this extra equation, make V the subject of the formula. Your V is Q upon C. Okay, substitute Q upon C for V here and C. So W is equal to half, I will keep Q, then instead of V I put Q upon C, okay. Q times Q will be Q square, so I have 1 over 2 Q square over C. So I have the third equation: work is equal to half Q square over C. Okay, you can use any one depending on what you are given. Let's see that in a few examples. Okay, look at this one. It says calculate the work done on a capacitor that stores a charge 40 millicoulomb when the PD across it is 80 volt. So here you are given the charge. Okay, let me use the other one. You are given the charge here, and your charge, this is your Q, and then you are given V. So in solving this problem solution, identify the charge you are given. Q is equal to 40 millicoulomb. This milli is 10 raised to the power of minus 3, so you have 40 times 10 raised to the power of minus 3 in coulomb, and then you are given V is 40 volt. So work done is equal to half QV. You use the first formula, and this is equal to half, you know, your Q, and your Q is 40 times 10 raised to the power of negative 3 times V, and your V is 40. Okay, half is just 0.5, so I will just press 0.5 for the half, and then multiplied by 40 exponential negative 3, exponential negative 3, then multiplied by, wow, I'm sorry, this is 80, so we have 80 here, not 40, 80 times 80. Okay, this is 8 over 5, the decimal, this is 1.6. So the work done is 1.6. Remember, work is measured in joules, so the work done is 1.6 joules. Okay, here is the second problem on this. A PD of 100 volt is applied on a capacitor of capacitance 5 microfarad. Calculate the energy stored in the capacitor. Okay, here you know V, and then you know the capacitance C. Okay, so you use the other formula. Well, your V is 100 volt, your C is 5 microfarad, and this is 5 times 10 raised to the power of minus 6 farad. Now, do we use work is equal to half QV? Of course, we can't use this one because we don't know Q. But let's see, work is equal to half QV, but we are given only V and C. You see that? So this Q, remember your Q is CV. So you put CV instead of Q. And this is equal to half into CV. And then you still have V here. Okay, what is in the bracket is for the Q. And this is equal to half. We clear the bracket. We have C, V times V, V squared. So we know our C, we know our V. Now we substitute and say half times C. The C is 5 times 10 raised to the power of negative 6 times V, and the V is 100. The formula says square the V, we square the V. And this is equal to wow, good. So we have 0.5 for the half multiplied by 5 exponential negative 6, okay, then multiplied by 100 squared, 1 upon 40, so the decimal, this is equal to 0.025 joule. If you want it in scientific notation or standard form, it is 2.5 times 10 to the power of minus 2 joules. Okay, and finally the third problem on energy stored in a capacitor. It says that a 20 microfarad capacitor, okay, this is your C, capacitance of the capacitor, stores a charge of this, so you are given the charge, this is your Q. Wow. Connected when connected to a voltage source. Calculate the work done, this is your target variable. So solution, we are given C, and C is 20 microfarad. Then we are given the charge Q, and the charge Q is 6 millicoulomb. The microfarad, this we change it to 20 times 10 raised to the power of minus 6 in farad, and this is 6 times the milli 10 raised to the power of minus 3 in coulomb. Now, the work done is our target variable, and we have established that this work done is half QV, but we are given the Q, but we don't know V. So remember, your Q is equal to CV. Since you don't know V, make V the subject of the formula here, and your V is equal to Q over C. So instead of V in this formula, put Q over C. This is equal to 1 upon 2 Q, and then instead of V we have Q over C. Then this is equal to 1 upon 2 Q times Q, Q squared divided by C. Then now we can substitute. This is 1 over 2 times q squared. What is q? This is q. Open bracket 6 times 10 to the power minus 3, that is our q, and the formula says square it, so we obey. Divided by c, and the c is 20 times 10 raised to the power of minus 6. Okay, how do we simplify this? Okay, look at it here. I'm going to open a bracket here. I open a bracket and press 6 exponential minus 6 exponential minus 3 close bracket, then I square it. See that? Divided by, okay, I have to start with this 2 again. 2 times 20 exponential this, so I will open a bracket for the denominators as well. I have 2 times this 20 exponential negative 6 negative 6 close bracket. This time I don't have a square, so I press this and then the SD. This will give me 0.9. This is 0.9 joule. Okay, this is the end of today's video, and I hope you understand how to derive the formula for work done or energy stored in a capacitor, and also how to use that to solve problem. Thank you for watching, and do not forget to subscribe. Assalamu alaikum wa rahmatullah.